Happy day, everyone. Welcome back. I hope you had a nice, restful weekend. I thought today we could start off with, believe it or not, some whiteboard review. You don't have to do it in your whiteboards, but I do recommend doing these problems, and I will give some time for you to think about them, but not very much because they're supposed to be the things that we kind of know now. So let's get into it. Log base b of 1. What's log base b of 1? 5, 4, 3, 2. If you're not sure, you can always do scorpion tail and rewrite this as an exponential, but it would be good if you knew at this point that that's 0. And if we think about this graphically, on the log graph, we have a reference point, 1, 0. So we know whenever we try and plug a 1 into log, we get a 0 as an output. Okay, log base b of 0. 5, 4, 3, 2, 1. Not possible. We should know this as where the vertical asymptote is on our regular log graph, and so that function can't exist there. How about log base b of b? 5, 4, 3, 2, 1. If we do scorpion tail here and write this as log base b, well, no, that wouldn't be scorpion tail at all, Mr. Kukla. Sorry about that. Let's put a little arrow here and say b to the question mark equals b, and so question mark equals 1. So we know then that this would have to equal 1. How about log base b of b to the n? That one's going to be very important today. 5, 4, 3, 2, 1. And we should end up with n. I'm wondering how many people did this problem this way. Log base b of b to the n equals question mark, and then scorpion tail to get b to the question mark equals b to the n, and so question mark equals n. That's one approach to this problem. But another thing that we talked about on Friday was that log base b and b raised to the power of were inverses of each other. Log base b and b to the power of are inverses of each other, and they're going to undo each other, and so we're just going to be left with n. That's also a fine way to do this problem. Today, I think we're going to see a third way to think about this problem, but not quite yet. First, we have to get our log properties. And how about this? We have two more. Log base b of a negative number. 5, 4, 3, 2, 1. Not possible. On our log graph, we've got that vertical asymptote at x equals 0. And all our graph is on one side of that vertical asymptote. There's nothing over here. Nothing. So I can't take the log of a negative. Now that doesn't mean I can't plug negative numbers into logs. For example, if I had this log graph, plugging negative numbers into that log graph is fine. I get, when I plug in -2, I get this value. And -3, I get this value. So it's not plugging negative number in that's a problem. It's I can't take the log of a negative number, and that too will be important today. All right, last one. Log b raised to the log base b of n. 5, 4, 3, 2, 1. Well, this should be n because b to the power of and log base b are inverses and undo each other, and so we're left with just n. Okie doke. All right, well, let's move on to a review of using the one-to-one property. Remember, we said that 3 to the No, I'm sorry, I wanted to do this as a log problem. Log base 3 of 81 equals question mark. So let's imagine we have to solve this equation. We talked about scorpion tailing it, about rewriting the log as an exponential. And then we wanted to rewrite the base so the bases were the same on both sides. So 3 to the question mark equals 3 to the fourth, and question mark equals 4. This is called using the one-to-one property because the terms are supposed to be equal, the bases are the same, therefore the exponents must be the same. Okay, well let's see how we can apply that directly with logs rather than necessarily having to try and do a scorpion tail kind of thing. What if we have log 2x plus 1 equals log 3x minus 5. Okay, so I'm wondering when this log graph, which has been shifted left a half, intersects this log graph, which has been shifted right 5/3. Well, let's take a look. I wanted to use the one-to-one property here. Look, because these things are equal, the logs are the same, the bases are the same, and those of you wondering what happens when the bases aren't the same, you won't see that until at least Friday. So don't stress about that at this time. I don't even know that we'll see it ever, so shh. Okay, so here, since the logs are the same and their bases are the same and the terms are equal, that means this stuff in parentheses, 2x plus 1, should equal 3x minus 5 according to the one-to-one property. Now it's an algebra 1 equation for me to solve by getting all the x's onto one side and moving all the not x stuff to the other side. And I get x equals 6. But here's something we know about logs. Logs are must checks. Logs are must checks. Remember, we can't take the log of a negative and we can't take the log of 0. So if I take this 6 and plug it in here, 12 times 2 is 12, 6 times 2 is 12, plus 1 is 13. So I've got log 13 over there. And on the other side of the equation, 3 times 6 is 18 minus 5 is also log of 13. What I'm looking for is, are either of these 0 or negative? And I think the answer is no to that, so we're good to go. This is our answer. At x equals 6, these two log graphs intersect. Now, there's a second way for me to think about this problem without using the one-to-one property, and this is going to be important with what we do tomorrow, and it deals with the fact that logs and exponentials undo each other. So I'd like to introduce you to a new verb. It's called exponentiate. It's our new verb of the chapter. And so when I look at this original problem, log 2x plus 1 equals log 3x minus 5, I want to get rid of these logs so I can have access to these x's. Well, I don't divide by log to get rid of them. I have to exponentiate with the log base. Now, when I don't see a base written here, we know that that's the common log, or base 10. So I'm going to exponentiate on both sides with 10. Notice I'm using 10 as a base, and I've turned this log statement into an exponent on that 10. 10 is the base, and I've used this log as the exponent of that base. Why did I want to do that? Well, because remember, 10 to the power of log base 10 are inverses and undo each other. And so I'm left with 2x plus 1. And over here, this is also log base 10 and 10 to the power of, and they'll undo each other, and 3x minus 5. Now, I know it feels like one-to-one property is much faster and simpler. Why do I want to do this exponentiating thing? Well, I'm just going to say that exponentiating is much more common for where we're headed in the next few days, and so I thought I would show you both today. Okay, so let's do some more of this solving. And I don't particularly care for these if you're thinking about it using the one-to-one property or if you're exponentiating. So log base 4 of x plus 3 equals log base 4 of negative x plus 1. Why don't you try this problem and see what you get? I'll try it on mine, and in a few minutes, or in a minute, we'll share our answers. Five, four, three, two, 1. I wonder how many of you exponentiated on both sides. Again, I don't particularly care for these problems today. Starting tomorrow, exponentiating is going to be more important, so I practiced exponentiating. Remember, you use that base as a power on both sides. Yes, this base has to be the same, or else you couldn't use the one-to-one property either. And then these cancel, leaving me x plus 3 equals negative x plus 1. And we solve for x, and we get x equals negative 1. Now remember, this isn't a problem for us. We're not worried about getting x equals a negative number because look, when we must check this, remember, logs are must check. Exponentials are ought check because they have an unrestricted domain. But logs have a restricted domain, so they're must check. When I plug that negative 1 in, I get log base 4 of 2 on both sides. Well, I can take the log of a positive number. It's when I have a 0 at this point or a negative at this point that I have to throw this answer away. So here's my answer, x equals negative 1. Okay, let's try one more. How about this one? Log base 7 of x squared minus 14 equals log base 7 of 5x. Give this problem a try. I'll do it on my whiteboard and then we'll compare. And after that, we'll move on to talking about our log properties. Five, four, three, two, 1. Well, I exponentiated on both sides again, and these will cancel, leaving me x squared minus 14 equals 5x. Remember, whenever we have a quadratic, we want to move everything onto one side of the equation and have that equation set equal to 0. I then factored that trinomial. Good thing we've been practicing our factoring. And I got x equals 7 and x equals -2. But remember, logs are must checks. And it's not the presence of the negative number that's a problem. It's what happens when we plug these numbers in. So I have to check both the positive and the negative values. When I plug in the 7, I get log of 35 equals log of 35. I can take the log of a positive number, so this one works. But when I plug in -2, I end up with 4 minus 14, or the log of -10. I can't take the log of a negative number, so -2 is an extraneous solution here. So I only have one solution, x equals 7. Okay? Tomorrow and the next day, our focus will be exclusively on solving equations, both log and exponential ones. Today, we were just warming up with that. I want to switch now to talking about our official log properties. We've got 3 of them. We've got the product property, and the product property says when you've got a log plus another log, and the logs have the same base, you can rewrite this as one log where those objects are joined with multiplication. So if I see log base 3 of 4 plus log base 3 of 5, I can rewrite that as log base 4 of, of 3, 4 times 5, or log base 3 of 20 by using my log properties. Okay? We could also see this with ln. ln of 3 plus ln of 2 is going to be ln of 3 times 2, or ln of 6. There's our product property. The product property is not about a plus inside the log. It's about a plus between 2 separate logs, and I'm going to join those 2 logs as one log with multiplication. Multiplication for our product property. Okay, there's the product property. What about our quotient property? For the quotient property, I'm still going to be working with 2 logs, but this time, instead of 2 logs joined with addition, I'm going to be looking at 2 logs joined with subtraction. And in this case, I can rewrite this as one log, log base 3 of a over b. It's a quotient property, not a product property. So I'm going to be dividing. This is about getting 2 logs joined with subtraction to become one log where I see some division. So if I see log base 3 of 24 minus log base 3 of 6, I know that's going to be log base 3 of 24 over 6. Ooh, and I can even simplify that to be log base 3 of 4. Okay? So there's our quotient property. And yes, of course, it works for ln's as well. ln of 3 minus ln of 2 equals ln of 3 halves. All right? And you should be comfortable taking 2 logs and writing them as 1. That's called condensing. But you should also be comfortable at looking at this log over here and expanding it into 2 separate logs. So we'll be condensing and expanding for the rest of class as soon as we're done with our last log property. Okay, our last log property is the power property. The power property. log base b of b to the n. Now, we already know what this is. We've done it with scorpion tail today. We've done it by taking b to the power of and log base b and crossing them out because they're inverses. But I'm going to do something different here. I'm going to take this power and bring it in front. In the presence of a log or ln, I can use my power property to take that exponent and bring it down in front. N log base b of b. We talked earlier today how log base b of b was 1, and so 1 times n is n. Didn't we get n earlier today when we did this as scorpion tail? Didn't we get n when we crossed off log base b and b to the power of? Well, I know you're saying, why do we need yet another way? Well, it turns out if I have log base 2 of 5 to the third, I can't cross these off. Oops, I can't cross these off. And scorpion tail isn't going to help me a whole lot. 2 to what power is 125? But what I can do is the power property. I can bring that 3 down in front like that. And so if I have something like log base 2 of x squared, I can use that power property and bring that 2 down in front. And if I have log base 2 of the square root of x, I know that that's equal to log base 2 of x to the 1/2 power. And because I can rewrite this radical as an exponent, I can now use my power property to bring that power down in front and get 1/2 log base 2 of x. Okay? So there's our power property. Remember, we also had the product property, where when I see 2 logs joined with addition, I can rewrite them as 1 log where there's multiplication between those elements. Or if I see 1 log that has things joined together with multiplication, I can split them into separate logs where I have addition. And we've got the quotient property. When I see 2 logs joined with subtraction, I can rewrite that as 1 log where there's division between those 2 elements. Likewise, I should be able to look at this 1 log with the division in it and break it up into 2 separate logs with subtraction between them. Okay? So those are the things we're going to be practicing now. We're going to first be expanding, and then we're going to be compressing. And if time permits at the end, I'd like to look at the change of base formula, which is something that people with older calculators will appreciate. Okay, so first, expanding. I'm going to do the first problem, and then you guys can do the next one. Or maybe I'll do the first 2. No, you should do one. Okay, so log base 5 of x squared y. The directions are to expand. Well, I see 1 log with multiplication between 2 things here. And so I think to use the product property. And first, to rewrite this as 2 separate logs joined with addition. And that looks great. But I want to look again and notice, oh look, I have a log, and I have this exponent. So I'm going to use the power property now to bring this 2 down in front. And so I'm going to have 2 log base 5 of x plus log base 5 of y. That is expanding this 1 log as much as possible. This would be our expansion. Any questions? I wish I was there to take them. So instead, since I'm not, I'm going to say, will you try this problem? Log base 5 of 3xy. Try that one, and then we'll have a countdown, and we'll go over it together. 5, 4, 3, 2, 1. Well, I saw a bunch of things multiplied together here. So I just wrote this as log base 5 of 3 plus log base 5 of x plus log base 5 of y. That's me expanding log base 5 of 3xy. Okay? How about you try this one now? Log base 5 of xy squared. Five, four, three, two, one. Well, this is a lot like the first problem I showed, where we would have log base 5 of x plus log base 5 of y squared. But in the presence of a log, I can use my power property to bring that exponent down. And so I would write log base 5 of x plus 2 log base 5 of y. Okie doke. All right, let's take a look at some others. Oh, hey, I wanted to say if I see something like this, which is similar to, but not the same as, log base 7 of xy squared, the power is outside of the product. So I actually have to use the power rule first, 2 log base 7 of xy, and then I can use my product rule, log base 7 of x plus log base 7 of y. And then distribute that 2 to each of these to get 2 log base 7 of x plus 2 log base 7 of y. You know, with this problem, we could also, if we go back to the original problem, we could apply this exponent to each of these and rewrite the problem as log base 7 of x squared, y squared, and then use the product property, log base 7 of x squared plus log base 7 of y squared, and then use our power rule not once, but twice to get 2 log base 7 of x plus 2 log base 7 of y. So these are the same problem. I can approach them two different ways, or two different ways of using the power rule. But don't confuse this problem with this one. This is the one that you guys just did, where you had log base 7 of x plus 2 log base 7 of y, and that's not quite the same as this. Okay, so let's take a look at some other problems. I'm sorry if I just erased that too quickly for you, but I wanted to look at log base 7 of 5xy. Okay, so I see here a product on top, but a quotient with the y. And so that's going to mean I'm going to do log base 7 of 5 plus log base 7 of x, because those are joined together with multiplication. And the y is being divided, so I'm going to do minus log base 7 of y. Okay? Why don't you try this one? Log base 3 of 5 over m. Please expand this log expression. Five, 4, 3, 2, 1. So I see the quotient here, and I think, well, I can use my quotient property and rewrite this as log base 3 of 5 minus log base 3 of m. Hey, what if we changed this problem slightly and turned it into log base 3 of 25 over m? How does that change this problem? Why don't you try that? 5, 4, 3, 2, 1. Well, we start off the same. Oops, not plus. We're not multiplying those together, we're dividing. Log base 3 of m. But look at 25. 25 is log base 3 of 5 squared. We've got some more expanding to do. I can use that power property to bring that 2 down in front. Log base 3 of 5 minus log base 3 of m. Okay? So make sure you expand as much as possible. So here's your problem then. Will you please expand this one? Log base 7 of 6 over xy. I'll give you a minute to do that one, and then we'll expand it together. Okay, let's see what you've got. 5, 4, 3, 2, 1. So I started this way. I started with log base 7 of 6. Now, notice how these are both in the denominator. I know that some of you say, but Mr. Kukla, these are attached with multiplication. Yeah, so here's what I want to do. I want to do log base 7 of x minus log base 7 of y. And I can just hear some students saying, but Mr. Kukla, these are multiplied together. Why isn't there a plus there? Well, check it out. There can be a plus there if you write the problem this way. Log base 7 of 6 minus log base 7 of xy. And now for this, write log base 7 of 6 minus log base 7 of x plus log base 7 of y. So there is that plus there, but I've also got this minus out in front. That minus is going to need to be distributed. So log base 7 of 6 minus log base 7 of x minus log base 7 of y. Now, I will tell you that for my brain, I think it's easier to say if things are on the bottom, then they're going to have minuses. If things are on the top, then they're going to have pluses. Are we done with this expansion? Oh no, look, that's a product. That's a product of 2 times 3. So I'm going to have to use the product property there to break up 6. So we're going to have log base 7 of 2 plus log base 7 of 3 minus log base 7 of x minus log base 7 of y. And there's our full expansion. Wow, there was a lot to that problem. So, no, that's not an unreasonable test question. That's actually very reasonable. It does require us to pay attention, and it does require us to use both the product and quotient rule. Okay? So how about you... No, how about I'll show you 1 or 2 now. How about I show you 1 or 2? We'll do 1 or 2 more with whiteboards, and then we'll move on to condensing. Okay, so I wanted to show you log base 6 of 1 over z to the third. Okay, so I can look at this problem two ways. One way is I can flip that up and turn this into log base 6 of z to the negative third power. And then I can use that power property to bring the negative 3 down in front. Log base 6 of z. And there I could be done. Or I could think about doing this problem this other way, where I see a quotient here. And if I see a quotient, I could write this as log base 6 of 1 minus log base 6 of z to the third. I see the opportunity to use the power rule. Log base 6 of 1 minus 3 log base 6 of z. And remember from our start today, we said log base b of 1 was 0. So we've got 0 minus 3 log base 6 of z. And instead of writing that 0, I'm just going to write negative log base 6 of z. I don't care which method you use for this problem. Both are appropriate and fine. I'm happy with you just being comfortable with at least one of them. Okay, the next one I want to look at is log base 3 of cube root of x over 3y. Okay, there's a lot going on here. And I think it may be useful to rewrite that cube root as an exponential. Log base 3 of x over 3y to the 1/3 power. This allows me to use that power rule and bring that 1/3 down in front. Oops. Log base 3 of x over 3y. And now, remember what I said, if it's on top, I'm going to have a plus, and if they're on the bottom, we're going to have minuses. So I'm going to have 1/3 log base 3 of x minus log base 3 of 3 minus log base 3 of y. All of this, of course, has to have that 1/3 distributed to it, but I want to look at something first. What's log base 3 of 3? Remember from our opening today, we said that that was going to be 1. Log base b of b is 1. So I can write this like this. And now I'm going to distribute that 1/2 and get 1/3 log base 3 of x minus 1/3 minus 1/3 log base 3 of y. There's my complete expansion. Okay, now I think you guys will do 2 more, and then we'll switch to condensing. Okay, here's your first one. ln 5th root of t. That's a 5. ln of the 5th root of t. Take a moment to think about how to rewrite that and then expand using your properties. Five, 4, 3, 2, 1. So I like here rewriting this with rational exponent 1/5 and then using the power rule to bring that power down in front. And that's all I can do. That's as expanded as I get here. Okay? How about you try this one? A little more. ln of square root of x, y, z to the third. The square root is only over the x, not the y or the z to the third. Try expanding that as much as possible. 3, 2, 1. So I expanded first with the product rule, ln square root of x plus ln of y plus ln of z to the third. And then I saw the power rule could be used over here, and so I brought down that 3, and I had ln of y, ln square root of x, and 3 ln of z. Are we done? No, we can't leave this here because this could be rewritten as x to the 1/2 power. And that means I need to use the power rule there. So I'm going to have 1/2 ln of x plus ln of y plus 3 ln of z. Okie doke, there's expanding logs. All right, let's take a look at doing some condensing problems now, where we have 2 or more logs and we want to join them into one if possible. Let's take a look. We'll start off gently and get a little more complicated as we go. I've got ln of 2 plus ln of x. 2 logs joined with addition. That means I can condense this into one log where those things are joined with multiplication with the product rule. Likewise, if I see the ln of y minus the ln of t, I see 2 logs joined with subtraction, and I know using the quotient property, I can rewrite this as 1 log where I join those things with a quotient, with division, okay? So what can you do with 3 log base 2 of x plus 4 log base 2 of y? Do you see anything you can do there? Well, before we do this product rule, we have to take care of these powers. So I'm going to kick these powers back up with the power rule in reverse and have log base 2 of x to the third plus log base 2 of y to the fourth. And now, because of this, I can use my product property in reverse and write this as log base 2 x to the third y to the fourth. Okay? So, why don't you try this one? 1/4 log base 3 of 5 plus 1/4 log base 3 of x. You try this one in a moment. We'll do a countdown and we'll take a look at it together. Five, 4, 3, 2, 1. Okay, so power rule in reverse first. Remember, when we're expanding, we do the power rule last, but when we're condensing, we do the power rule first. So I've got log base 3 of 5 to the 1/4 plus log base 3 of x to the 1/4. Now, because of this, I can use the product property in reverse and get log base 3 of 5 to the 1/4 times x to the 1/4. Now I'm actually going to use one of my exponential properties. Notice how both of these bases have the same power. Well, I'm going to pull that power out and write this as log base 3 of 5x to the 1/4. And then if you like, you don't have to, this is a fine place to stop, you could take it even back to 4th root of 5x for all of those things. So I would like one of these two as your final condensed answer. Okay? Let's take a look at another. If I have log base 2 of x minus 3 log base y, log base 2 of y, and plus 3 log base 2 of z, what can I do here? Well, I notice I've got some powers to kick up, and so that can be rewritten as log base 2 of x minus log base 2 of y to the third plus log base 2 of z to the third. Now, be careful here. This is the minus. This one goes on the bottom. I know this one comes after this and there's a plus and you really want to multiply these together, but no, pluses go on top. Look, we could rewrite this. Think about it as a minus b plus c. We could rewrite it as a plus c minus b. Look, now these two have the plus. We could write this as log base 2 of x plus log base 2 of z to the third minus log base 2 of y to the third. See, these are the ones that are going to be multiplied together. Anything with a plus is going to end up on top. Log base 2 of x z to the third, and with a minus goes to the bottom, y to the third. And so there's my answer. There's my condensed form of this expression with 3 logs in it. Okay, so will you try this one? Log base 2 of z minus 2 log base 2 of y minus 3 log base 2 of x. Take a moment to do that problem, and then we'll move on. Okay, so power property in reverse, and we have log base 2 of z minus log base 2 of y squared minus log base 2 of x to the third. Anything with a minus is going to go in the denominator. Remember, don't write this as log base 2 of z over log base 2 of y squared x to the third. That is a huge mistake. No. Remember, we're condensing to 1 log. Our property allows us to take these 2 logs and condense into 1. So I'm going to have log base 2 of z over y squared x to the third. All right. So what about this one? What if I see 2 bracket 3 ln of x minus ln of x plus 1 minus ln of x minus 1. What can I do here? Well, I can certainly kick that up with the power rule in reverse. I'll have ln of x to the third minus ln of x plus 1 minus ln of x minus 1. And then I see these can be condensed into 1 ln with x to the third on top and an x plus 1 times an x minus 1 on the bottom. Both of these go on the bottom and are multiplied together. Remember, you could always factor out that negative 1 from these two terms and have ln of x plus 1 plus ln of x minus 1. And look, see, that means they're supposed to be multiplied together. Remember, you still have this 2 out in front here. Well, I see then that this could be, bring that 2 up. I have x to the third. Ooh, look, foiling. x squared minus 1 squared. And I guess I could apply this as ln of x to the 6th over x squared minus 1 squared. Whew. I would accept either this one or this one as fully condensed. Okay? All right. Well, we only have a couple minutes left, so I want to do one or two quick things with you. First, the change of base formula. Those of you with older calculators definitely need this. Newer calculators allow you to evaluate things like log base 2 of 3 on your calculator. But if we have an older calculator, we definitely can't do that on our calculator. So I want to show you a recipe for being able to rewrite a log that has an inconvenient base. So maybe I want this to be the common log, base 10, or maybe I even want it to be ln. So what I'm going to do is I'm first going to think about this as question mark. And then I'm going to rewrite this 2 to the question mark equals 3. Now what? Well, I want to get this exponent down, but I can only have a power rule in the presence of a log. So just like we talked about exponentiating both sides earlier today, I'm going to take the log or ln of both sides. If I take the ln of both sides, I now have a log and I can bring the power rule down and say question mark ln of 2 equals ln of 3. Well, this question mark is attached to ln of 2 with multiplication, and so question mark equals ln of 3 over ln of 2 because I'm going to divide both sides by ln of 2. So how did we start? What is the point of this again? Well, we started with log base 2 of 3, and we wondered how we could rewrite this as something with a different base. Instead of base 2, I wanted to have ln's. I can't evaluate this with my old school calculator, but I can using the change of base formula. Change of base formula. I can rewrite this as ln of 3 over ln of 2. In fact, I didn't have to take the ln of both sides of the equation back up here. I could have taken the log of both sides and written log of 3 or over log of 2. So I don't expect you to go through this process when you need to use change of base formula. What I would like you to do is when you see log base b of a and you want to rewrite that, you can rewrite that as ln of a over ln of b or log of a over log of b. Okay, that's our change of base formula right there. And that may be useful in some of the homework problems tonight. Okay? And I think we might have 2 or 3 more minutes, so I'm going to do one last type of problem with you. And that looks like this, where they give me some information in the beginning, and they say, for example, log base 2 of 3 equals 1.585, and log base 2 of 7 equals 2.807. Okay? And then they say, hey, evaluate this. Log base 2 of 48 over 49. Well, I guess I could pull out my calculator and just ask it, and even if I have an old calculator, I could always rewrite this with the change of base formula. But what they're asking me to do here is to do an expansion. They want me to first rewrite this as log base 2 of 48 minus log base 2 of 49. And then to break each of these down. Now, I know that 48 is 16 times 3, and 49 is 7 squared. So I see I can pull that 2 down in front, minus 2 log base 2 of 7. But over here, I see another product. So I'm going to split this up into log base 2 of 16 plus log base 2 of 3. 16 is, of course, 4 squared. Log base 2 of 4 squared plus log base 2 of 3 minus 2 log base 2 of 7. Bring that 2 down in front. 2 log base 2 of 4. Oh no, look at 4. You know, we're going to have to do some more. Maybe it would have been smart if back here we saw 16 as 2 to the 4th. Because then we could just bring down this 4 and have a 2 here. Plus log base 2 of 3 minus 2 log base 2 of 7. Well, what's log base 2 of 2? Log base b of b is 1. 1 times 4 is 4. Log base 2 of 3, they told us up here in the start of the problem, was 1.585, and then we have minus 2, log base 2 of 7, they also gave me 2.807. So I can evaluate this 5.585 minus 5.614, and I end up with the slightly negative number 5 minus 5.614, and I get negative 0.029. Okie doke. And that makes sense to me because the log of a number between 0 and 1 on our log graph is over here. It's going to be a negative value. So you may see a couple problems like this in tonight's homework where you need to do expanding. I hope this helped. I hope this was useful. Don't forget to send me your questions and comments for improving this process. I'll talk to you soon, and good luck with your homework. Take care.